Einstein's quantum riddle, the mystery of entanglement. Imagine, if you will, lying on your back beneath a velvet sky. The stars above glimmer as if someone has scattered diamond dust across an infinite canvas. They seem so far apart, impossibly distant, and yet, what if I told you that, in a hidden language of nature, 2 points of light, no matter how separated, could whisper to one another instantly, without wires, without signals, without even the permission of time itself? Albert Einstein called this phenomenon spooky action at a distance. To him, it seemed absurd, even offensive to common sense. And yet today, we call it quantum entanglement, and it's not just a thought experiment or a mathematical oddity. It is as real as the stars, as mysterious as dreams, and as powerful as the technologies it now inspires. In tonight's journey here on Sleep Entangled, we will drift slowly, gently, through the story of quantum entanglement, its origins, its paradoxes, its experiments, and the revolutions it promises. We will revisit Einstein's doubts, the triumphs of modern physics, and the breathtaking experiment across the Canary Islands that tested the universe itself. But before we unravel the threads of this quantum riddle, allow me to gently invite you, if you find wonder in these late-night voyages, if you feel comfort in these quiet explorations of science and mystery, to subscribe to this channel, Sleep Entangled. It helps me continue weaving these soft-spoken journeys and ensures you never miss the next drift through reality's hidden layers. Now, let us close our eyes, relax our breath, and let the story begin. Chapter 1. Introduction. Quantum physics is not just science. It is poetry written in equations, paradoxes, and possibilities. It forces us to see the universe not as a stage filled with predictable actors, but as a shimmering sea of uncertainty, where every particle is both a wave and a possibility, a secret waiting to be revealed. Entanglement is perhaps its strangest chapter. Imagine 2 particles born together, like twins separated at birth. You send one across the universe to drift among galaxies, while the other stays with you, nestled here on Earth. Intuitively, you might think, distance breaks connection. After all, a message takes time, a signal must travel. Yet quantum physics tells us that these twins remain connected in a way that defies space itself. Measure one, and instantly, the other seems to know. Their properties mirror each other, as if distance were irrelevant, as if the cosmos itself were folded into a single, shared secret. This is the riddle that unsettled Einstein. He believed deeply in locality, that nothing could influence something else faster than the speed of light. The very bedrock of his relativity depended on it. To suggest otherwise seemed impossible, almost heretical. And yet, physicists began to uncover hints that the universe did not care about our intuition. The mathematics predicted entanglement. Experiments whispered its truth. And slowly, reluctantly, scientists realized that what Einstein dismissed as spooky action might in fact be one of the most fundamental features of reality. But before entanglement came to light, the world of physics itself had to break apart and rebuild. Let us gently rewind to the dawn of the 20th century. Classical physics, the physics of Newton's clockwork universe, had dominated for centuries. According to Newton, the universe was like a vast machine. If you knew the position and velocity of every part, you could, in principle, predict the future with perfect accuracy. Certainty reigned. Cause led to effect, like gears turning in a grand celestial watch. Then came cracks in the clockwork. Light, for example, refused to obey. Sometimes it behaved like a wave, spreading across space in graceful ripples. Sometimes it behaved like a particle, a stream of discrete quanta. No matter how physicists tried to pin it down, light danced away, refusing to fit into a single box. Max Planck, in 1900, introduced the radical idea of energy quanta, tiny packets of light, indivisible and precise. His insight solved a puzzle known as the ultraviolet catastrophe, where classical physics predicted absurd infinities. But Planck himself did not quite believe the full implications. A few years later, Albert Einstein expanded the idea, explaining the photoelectric effect, how light shining on a metal surface could release electrons, like marbles struck from a table. Crucially, the effect depended not on the intensity of light, but on its frequency. A dim ultraviolet ray could liberate electrons, where a bright red beam failed. Light, Einstein proposed, came in quanta, what we now call photons. This dual nature, wave and particle, was unsettling. It was as if reality refused to commit to one identity, preferring instead to exist in superpositions, in probabilities. From here, the quantum revolution accelerated. Schrödinger introduced his wave equation, describing particles not as points, but as waves of probability. Heisenberg showed us the uncertainty principle, that position and momentum could never both be known precisely, no matter how refined our instruments. And then, nestled in this strange new world, was entanglement. Einstein, together with Podolsky and Rosen, crafted what is now known as the EPR paradox. They argued that quantum mechanics, though powerful, must be incomplete. Surely hidden variables existed, unknown rules beneath the surface that preserved locality and determinism. To Einstein, the universe was not random, and it certainly was not instantaneously connected across distance. God does not play dice, he famously declared, but time and experiment would reveal otherwise. Stone's entanglement remained a philosophical puzzle for decades. Many physicists preferred to focus on the practical. The calculations worked, the equations predicted results, so why worry about the strangeness beneath? Shut up and calculate, some said, when confronted with questions about meaning. Yet the questions lingered. Was reality truly non-local? Could particles really remain linked across galaxies? And if so, what did this mean for our understanding of information, causality, and the very fabric of the cosmos? Fast forward to the late 20th and early 21st centuries, and these questions moved from the chalkboard to the laboratory. Scientists devised ingenious experiments to close loopholes, to test entanglement with ever more rigor, and perhaps the most breathtaking of these was staged in the Canary Islands, where light from distant quasars, billions of years old, was enlisted to help answer the question, is quantum entanglement real, or is it an illusion? That is the journey before us tonight. From Einstein's doubts to modern confirmations, from spooky action to quantum computers, from paradox to promise. A journey through the strange, the unsettling, and the beautiful. So as you settle deeper into rest, let your imagination drift alongside photons across vast distances, through the hidden channels of quantum connection. Together, we will explore not just physics, but philosophy, not just science, but wonder. And remember, in this universe of entanglement, perhaps you are never as alone as you think. Chapter 2: Is Quantum Entanglement Real? The Canary Islands Experiment. As we drift deeper into the universe's hidden layers, imagine yourself standing on a quiet volcanic ridge in the Canary Islands. The night is calm, the Atlantic breeze brushing softly against your face, and above you, telescopes tilt gently toward the heavens. These aren't ordinary telescopes. They are instruments poised to peer back billions of years, capturing the faint light of quasars at opposite ends of the cosmos. And through them, scientists seek to answer a question that has haunted physicists for nearly a century. Is quantum entanglement real? The idea seems almost magical. Two particles, born together in a laboratory, are sent apart. One drifts here on Earth, the other, perhaps, on a distant satellite, or even a spacecraft millions of miles away. Measure one particle's spin, its polarization, its energy state, and instantaneously, without delay, the other particle mirrors that state. Across any distance, the link remains unbroken. Einstein famously recoiled at the notion, calling it spooky action at a distance. To him, it was inconceivable that nature could allow instantaneous connections across the void. The speed of light, after all, was supposed to be the cosmic speed limit. Yet quantum mechanics insisted otherwise. It whispered of a universe where entangled particles share a secret bond, a thread invisible yet unbroken, defying classical intuitions about space, time, and information. And so scientists devised tests, carefully designed to probe the universe itself. One of the most ambitious and beautiful was set in the Canary Islands. Here, teams aimed to use quasars, ancient beacons of light from the earliest galaxies, as cosmic randomizers. Why quasars? Because their light has traveled billions of years across the universe, predating our very existence, their photons untouched by earthly influences. If we can use these distant, independent signals to determine how to measure entangled particles here on Earth, we can close a critical loophole. No hidden influence from the past could have cheated the experiment. Imagine the setup. Two laboratories, separated by a mountain ridge, each containing a particle from an entangled pair. Hundreds of millions of photons have been emitted by quasars long before our sun even formed. The photons strike detectors that randomly determine how each laboratory will measure its particle. Then, in an instant, entangled particles reveal their correlations, perfectly aligned with quantum predictions. This experiment, elegant and poetic, does more than confirm quantum mechanics. It confronts one of the deepest questions about reality. Could entanglement be explained by some hidden mechanism, some unseen variable acting locally? Or is the universe truly non-local, as quantum theory suggests? The results were stunning. No classical explanation could account for the correlations observed. The particles behaved as if their fates were intertwined, regardless of distance, ignoring every conventional rule of causality. Einstein's discomfort remains a historical echo, but the evidence is now overwhelmingly clear. Quantum entanglement is real. It is not a trick of mathematics or an artifact of experimental error. It is a fundamental feature of our universe. But let us pause here and consider what this means, gently, as you relax into your pillow, letting the waves of thought wash over you. This spooky action is not just a quirky phenomenon confined to physics textbooks. It is the thread that will weave new technologies, the foundation for quantum computers capable of solving problems classical machines cannot, the backbone of quantum cryptography securing information in ways previously unimaginable. And yet, it is also a profound meditation. If the universe allows such instantaneous connections, what does that say about our classical sense of separation? Perhaps the cosmos is less a collection of isolated objects and more a tapestry of interwoven events, each particle, each star, each consciousness subtly influencing another across space and time. Returning to the Canary Islands, the experiment embodies this principle beautifully. By reaching for the distant quasars, the researchers are not merely measuring photons, they are measuring the cosmos itself, testing the very structure of reality. The universe responds with a whisper, yes, entanglement exists, and it connects us all in ways we are only beginning to understand. Let us now slow our breathing and imagine the paths of the entangled particles, curving invisibly through space, each measurement a gentle collapse of possibility into reality. One particle spins up, the other spins down, as if sharing a secret encoded in the very fabric of existence. And while we watch, from our soft beds or quiet chairs, we realize that the universe has rules far stranger, far more beautiful than our daily experience suggests. Historically, this experiment builds on a century of inquiry. After Einstein, Podolsky, and Rosen formalized the EPR paradox in the 1930s, physicists like John Bell began asking, could these entanglement correlations be explained without invoking spooky action? Bell formulated inequalities that could be tested experimentally, bridging theory and reality. Subsequent experiments, from Alan Aspect's pioneering work in the 1980s to the Canary Islands test, gradually closed loopholes and confirmed what quantum mechanics had always predicted. It is remarkable to think that these principles, once considered philosophical curiosities, now underpin real-world technologies. Quantum entanglement powers secure communications, allowing two parties to detect any eavesdropping, ensuring absolute privacy. In quantum computing, entanglement enables qubits to occupy multiple states simultaneously, vastly increasing computational power. The spooky connections that once troubled Einstein now promise to revolutionize the world. And as we let our minds drift, imagine the experiment from a human perspective. Picture the meticulous care of researchers adjusting detectors, calibrating telescopes, ensuring that every photon from a quasar millions of light years away, arrives precisely on schedule. Each photon, a messenger from the distant past, plays its part in testing one of the deepest truths about the universe. The elegance of this cosmic choreography is almost poetic, a dance across time and space that invites awe, reflection, and wonder. Yet with wonder comes humility. Entanglement challenges our very notions of reality. It tells us that measurement matters, that the act of observing changes the outcome, that the universe is more relational than absolute. It blurs the line between observer and observed, between here and there, now and long ago. And perhaps, as we drift deeper into rest, this gentle paradox can also teach us something about our own lives. That connections, even unseen, ripple across space and time, shaping outcomes in ways we cannot always perceive. So, as the Canary Islands experiment demonstrates, entanglement is not just a quirky prediction of mathematics. It is a real, measurable, and profoundly beautiful feature of the cosmos. Particles, like cosmic dancers, mirror one another across unimaginable distances. The universe whispers its secrets to those patient enough to listen, and tonight we are listening together. And as your eyelids grow heavier, let this thought settle gently into your mind. The universe is far stranger and more connected than our senses can perceive. Every particle, every photon, every quasar's light is part of a tapestry, a network of subtle, instantaneous connections stretching across space and time. With this calm awareness, let us prepare to explore the next layer of the story, the beginnings of quantum mechanics, the historical context that gave birth to these ideas, and the revolutionary minds who first glimpsed a universe where certainty is not guaranteed and the improbable is, in fact, possible. Chapter 3: The Beginnings of Quantum Mechanics. As the night deepens, let's drift gently back over a century to the dawn of a new scientific era, a time when the comforting certainties of classical physics were beginning to tremble. Imagine a world in which Newton's laws, Maxwell's equations, and the elegant predictability of classical mechanics seemed absolute. Every planet, pendulum, and particle could be described with precision, and the universe appeared like a vast, perfectly tuned clockwork. Yet by the turn of the 20th century, subtle cracks began to appear in this grand edifice. Scientists observed phenomena that simply could not be reconciled with classical rules. Heat radiation from glowing objects, the behavior of light itself, and the energetic emissions of atoms refused to align with old theories. One of the first and most remarkable cracks came from the study of blackbody radiation, the energy emitted by heated objects. Classical physics predicted an ultraviolet catastrophe, an impossible divergence in energy at short wavelengths. The equations suggested the universe would be awash in infinite energy, clearly contradicting reality. Enter Max Planck, a quiet, meticulous physicist who would forever alter our understanding of energy. In 1900, Planck proposed a radical solution. Energy is not continuous, as everyone had assumed, but quantized, existing in discrete packets he called quanta. Imagine stepping onto a staircase rather than a ramp. Energy doesn't flow smoothly, but jumps from one level to the next. This tiny adjustment, a mere shift in perspective, solved the ultraviolet catastrophe and laid the foundation of quantum theory. Planck's idea was revolutionary, yet at first, it seemed almost like a mathematical trick. Scientists were unsure if it represented reality or was merely a useful tool for calculations. But soon, other phenomena demanded a similar boldness of thought. Light itself revealed its dual personality. For centuries, light had been described as a wave, rippling elegantly through space. But in 1905, Albert Einstein proposed that light could also behave as particles, called photons, particularly in explaining the photoelectric effect, where shining light on a metal surface ejects electrons. The energy of these photons depended not on the intensity of light, but on its frequency, a subtlety that classical physics could not explain. Einstein's insight earned him the Nobel Prize in 1921, but more than that, it opened a doorway into a strange new world where certainty was no longer guaranteed. Light, and by extension all matter, could behave as both wave and particle. The universe, it seemed, was a realm of probabilities, where observation could influence outcomes in ways that defied common sense. Around the same time, experiments with atoms revealed further mysteries. Electrons, once thought to orbit the nucleus like planets around the sun, exhibited behaviors that classical orbits could not describe. Electrons exist in discrete energy levels, jumping unpredictably between them and emitting photons in the process. This led to the development of the Bohr model of the atom, a first attempt to reconcile classical mechanics with emerging quantum insights. Yet the full complexity of quantum mechanics was still unfolding. In 1925, Werner Heisenberg, working with the matrix formulation of quantum mechanics, proposed that at the smallest scales, exact predictions were impossible. There was always uncertainty, an intrinsic fuzziness woven into the fabric of reality. Shortly after, Erwin Schrödinger introduced the wave function, a mathematical object that described all possible states of a quantum system simultaneously. Instead of knowing a particle's exact position or momentum, physicists could now calculate probabilities, the likelihood that a particle would be found in a given state upon observation. Imagine for a moment standing before a vast ocean of possibilities. Every particle, every photon, every quantum system exists in a cloud of potential, like countless ripples overlapping, until an observation collapses this cloud into a definite state. Schrödinger famously illustrated this idea with his thought experiment, the infamous Schrödinger's cat, a creature both alive and dead, simultaneously, until the box is opened and reality collapses into a single outcome. The image may seem whimsical, even absurd, but it captures the deep strangeness of quantum mechanics. Reality at the smallest scales refuses to be pinned down by classical expectations. It was during these years that Einstein, Podolsky, and Rosen challenged quantum mechanics in the famous EPR paradox, questioning whether the theory could provide a complete description of reality. If entangled particles instantaneously affected each other across vast distances, as the theory implied, could this really be compatible with relativity? Could there be hidden variables, unknown factors that would restore classical predictability? This debate would echo through the decades, ultimately leading to experiments like the Canary Islands entanglement test we explored in the previous chapter. Meanwhile, other physicists were uncovering additional quantum phenomena. Pauli's exclusion principle revealed why electrons arrange themselves into shells around nuclei, giving atoms their chemical properties. De Broglie proposed that matter itself exhibits wave-like behavior, extending the wave-particle duality beyond light to all particles. Quantum mechanics, in other words, was not just about tiny particles. It was a revolutionary framework, reshaping our understanding of matter, energy, and the very structure of the universe. And as the theory developed, the strange implications only grew. Heisenberg's uncertainty principle declared that the more precisely we measure one property of a particle, the less precisely we can know another. There is no perfect knowledge at the quantum level. Superposition suggests that until observed, a quantum system exists in multiple states at once. Entanglement implies that separated particles share instantaneous correlations. These principles are not just abstract, they define reality itself. Yet despite this strangeness, the pioneers of quantum mechanics approached their work with both rigor and playfulness. They explored probabilities, equations, and wave functions with the delight of explorers charting unknown continents. And tonight, as you listen, you can join them in this gentle journey, feeling the wonder and awe of a universe that refuses to be simple, a cosmos that challenges our assumptions and invites curiosity. Now let's pause to reflect on how these ideas ripple into our modern lives. Quantum mechanics is not confined to chalkboards and laboratories. It powers technologies all around us. Lasers, semiconductors, MRI machines, and LEDs rely on principles born in this era. Without Planck, Einstein, Schrödinger, and Heisenberg, our modern world would be unimaginably different. Their insights, once purely theoretical, now touch every facet of our daily experience. And so, as your body relaxes and your mind drifts along this gentle stream of understanding, consider the poetic beauty of these discoveries. Each atom, each photon, is a universe of probabilities, dancing in a delicate choreography dictated by the strange but precise rules of quantum mechanics. We are immersed in a cosmos far more intricate and interconnected than classical intuition ever imagined. From the ultraviolet catastrophe to Schrödinger's cat, from Planck's quanta to Heisenberg's uncertainty, the beginnings of quantum mechanics mark the first awakening to a world of mystery, probability, and infinite possibility. It is a world that invites us to ponder, to imagine, and to marvel, even as we close our eyes and drift into sleep. And as we settle into this quiet contemplation, let the names of these pioneers, Planck, Einstein, Bohr, Schrödinger, Heisenberg, become gentle guides in your mind. Each contributed a stroke to the vast canvas of understanding, revealing a universe simultaneously predictable and unpredictable, orderly and mysterious, known and unknown. In the next chapter, we will explore how Einstein, Podolsky, and Rosen formalized their famous paradox, challenging these early discoveries and setting the stage for decades of experiments that would probe the boundaries of reality itself. But for now, let your thoughts float in the soft glow of quantum beginnings, letting the wonder of discovery lull you gently onward. Chapter 4: Quantum Mechanics Explained by Einstein, Podolsky, and Rosen. As we drift gently deeper into the quantum world, let us pause to consider a debate that has intrigued and challenged physicists for decades. It is a debate born from curiosity, skepticism, and a desire to understand the nature of reality itself. In 1935, Albert Einstein, Boris Podolsky, and Nathan Rosen, collectively known as EPR, posed a question that would echo through the corridors of physics for generations. Can quantum mechanics be a complete description of reality? To understand their concern, we must first appreciate the world they inhabited. Quantum mechanics was still in its infancy. Schrödinger had formulated his wave equation, Heisenberg had defined uncertainty, and the Copenhagen interpretation was gaining prominence under the guidance of Niels Bohr. This interpretation suggested that physical systems do not have definite properties until measured. Observation, it seemed, was fundamental, not just a passive act of seeing, but an active participant in shaping reality. Einstein, ever the realist, was uncomfortable with this. He famously said, "God does not play dice with the universe." He believed that the universe had an objective existence, independent of observers, and that there must be underlying hidden variables, unknown factors that could restore determinism to a world that seemed capriciously probabilistic. The EPR paper introduced a thought experiment designed to challenge the Copenhagen interpretation. Imagine two particles that interact and then move apart, perhaps even light years away from each other. According to quantum mechanics, these particles can become entangled, meaning their properties are linked in such a way that measuring one immediately affects the other, no matter the distance. Einstein, Podolsky, and Rosen argued that this spooky action at a distance, as Einstein called it, seemed impossible. If measuring one particle instantly influenced the other, would that not violate the speed limit set by relativity, the speed of light? And if the influence is real, then either quantum mechanics is incomplete, missing hidden variables, or the universe is deeply non-local in a way that defies intuition. At its heart, the EPR paradox forces us to confront profound questions about the nature of reality. When two particles are entangled, is the second particle's state determined only when we measure the first? Or does each particle carry pre-existing information about its state, waiting to be revealed? This was more than a philosophical musing. It was a challenge to the very foundations of physics. For decades, the debate remained largely theoretical. Philosophers and physicists argued, wrote papers, and conducted small experiments, but the technology to test the predictions conclusively did not yet exist. The questions were subtle and precise. Is entanglement real? Can particles truly influence each other instantaneously? Does reality have an underlying determinism, or is probability woven into the very fabric of existence? The EPR paper catalyzed a series of conceptual breakthroughs. John Bell, in 1964, formulated what are now known as Bell's inequalities, mathematical criteria that could be tested experimentally. If quantum mechanics is correct and entanglement is real, certain correlations between entangled particles would violate these inequalities. If the inequalities held, then hidden variables might still explain the outcomes. Bell's work transformed philosophical speculation into a question that could be tested in the laboratory. Experiments soon followed. Pioneering physicists like Alain Aspect in the 1980s set up entangled photon experiments that demonstrated correlations violating Bell's inequalities. The results were stunning. Quantum mechanics was correct, entanglement was real, and the universe allowed instantaneous correlations across space. Einstein's discomfort remained, a mystery at the deepest level, but the evidence was undeniable. Imagine the subtle beauty of these findings. Two photons, born together and then separated by kilometers, exhibit a perfect harmony. Measure one, and the other seems to know instantly, reflecting the measurement in its state. There is no classical signal traveling between them. It is as if the universe has a hidden thread, weaving particles together across vast distances in a silent, invisible tapestry. For our purposes tonight, we can appreciate the wonder without getting lost in the technical weeds. Entanglement is not science fiction. It is a reality that has been repeatedly confirmed. It challenges our intuition, but also opens doors to technological revolutions. Quantum cryptography, for example, uses entangled particles to create theoretically unbreakable codes. Quantum teleportation, not in the Star Trek sense of matter teleportation, but in transmitting the state of a particle instantaneously, is another practical application. Returning to the historical thread, the EPR paper also illuminated a tension between two ways of understanding nature. On one hand, the Copenhagen interpretation embraces uncertainty and observer participation. On the other, Einstein sought determinism and objective reality. This tension is not merely historical, it continues to guide research today, from foundational experiments to cutting-edge quantum computing. As you listen and relax, consider what this means for our broader understanding of existence. Quantum mechanics invites a radical perspective. Reality may not be a fixed stage on which events unfold. Instead, it may be a dynamic, participatory network where observation, measurement, and entanglement play central roles. Each particle, each interaction, is a tiny note in a cosmic symphony with patterns emerging across space and time. And yet, the EPR paradox reminds us of humility. Even with over a century of experimentation, we are still learning the rules of this intricate dance. Entanglement, superposition, and the probabilistic nature of particles are phenomena that defy everyday experience, reminding us that our intuitions, shaped by the macroscopic world, may not always apply. So as your body sinks deeper into comfort and your mind floats in gentle curiosity, you can visualize two entangled particles, perhaps photons or electrons, separated by the expanse of the cosmos, yet forever connected. Their dance is silent, invisible, but utterly real, a poetic echo of the quantum universe. It is a reminder that even at the smallest scales, nature is rich, surprising, and profoundly interconnected. And now, with this understanding, we can gently prepare to move to the next chapter, where we explore the developments that flowed naturally from the discovery of quantum theory. Here, we will see how early pioneers applied these ideas, conducting experiments that tested the limits of our understanding and paved the way for modern quantum technologies. But for now, breathe deeply, feel the quiet magic of entanglement, and let your imagination drift along these invisible threads of reality. Chapter 5: Developments from Discovery of Quantum Theory. As we continue our gentle journey through the wonders of quantum physics, it's time to explore the profound developments that emerged from the early discoveries of the 20th century. After the foundational insights from Planck, Einstein, Bohr, and the EPR team, physicists began to expand these ideas, testing, refining, and sometimes challenging the very core of what we thought we knew about reality. One of the most transformative advances was the formalization of quantum mechanics itself. Schrödinger's wave equation provided a mathematical framework to describe particles as wave functions, encapsulating probabilities rather than certainties. This was revolutionary. Instead of seeing an electron as a tiny solid object traveling along a predictable path, physicists now understood it as existing in a cloud of probabilities, a wave-like spread that only collapses into a definite location upon measurement. Simultaneously, Heisenberg introduced the uncertainty principle, revealing a fundamental limit. The more precisely we know a particle's position, the less precisely we know its momentum. Less precisely we can know its momentum, and vice versa. This wasn't a flaw in measurement, it was a property of reality itself. For the first time, physics embraced intrinsic uncertainty as a central feature of the universe, turning classical determinism on its head. Building on these insights, countless experiments tested the predictions of quantum theory. The double-slit experiment, for example, became a touchstone for understanding the wave-particle duality of matter. Electrons, photons, and other particles revealed interference patterns when unobserved, behaving like waves, yet appeared as discrete particles when measured. Each new experiment confirmed the strange, counterintuitive principles of quantum mechanics, deepening our appreciation for the universe's subtle complexity. Meanwhile, physicists explored entanglement, the phenomenon that had both intrigued and unnerved Einstein. Early experiments entangled photons, electrons, and other particles, verifying that changes to one particle immediately influenced its partner, no matter the distance. These experiments not only confirmed EPR's thought-provoking paradox, but also laid the groundwork for modern quantum technologies, including secure communications, quantum computing, and precise measurement techniques. As the mid-20th century approached, the need for a unifying framework became clear. Enter quantum field theory, QFT, which treated particles not as independent entities, but as excitations of underlying fields. The electromagnetic field, the electron field, and other fundamental fields became the stage upon which the universe's interactions played out. This elegant perspective allowed physicists to predict phenomena with extraordinary accuracy, from the magnetic moment of the electron to subtle scattering effects. Within QFT, the standard model of particle physics emerged, cataloging the fundamental particles, quarks, leptons, and bosons, and the forces that govern their interactions, including electromagnetism, the strong and weak nuclear forces, and the recently confirmed Higgs field. The Higgs field, in particular, explained why particles have mass, acting as a kind of medium through which particles move, slowing them down and giving them substance. Imagine moving through a viscous fluid where resistance imparts a tangible quality. This is a helpful analogy for how the Higgs field operates. Yet despite its successes, the standard model remains incomplete. Gravity, dark matter, and dark energy elude full explanation, reminding us that the universe still holds deep mysteries. The challenge of unifying quantum mechanics with general relativity continues to inspire theoretical physicists, guiding research into string theory, loop quantum gravity, and other ambitious frameworks. Amid these theoretical breakthroughs, technology began to harness quantum principles in practical ways. Quantum computers emerged, leveraging superposition and entanglement to perform computations far beyond classical limits. Unlike classical bits that exist as 0 or 1, qubits can occupy multiple states simultaneously, enabling exponential increases in processing power. While large-scale quantum computers are still in development, prototype systems are already solving specialized problems such as optimization, complex simulations, and cryptography. The influence of quantum mechanics extends beyond physics laboratories. Researchers discovered that quantum phenomena appear in biological systems, giving rise to the field of quantum biology. Birds navigate using the Earth's magnetic field, aided by quantum entanglement in their retinal proteins. Plants optimize photosynthesis through quantum coherence, efficiently transferring energy in a way classical physics alone cannot explain. These discoveries suggest that life itself may be fundamentally quantum, revealing a universe more interconnected than previously imagined. In addition to practical applications, these developments forced us to confront deep philosophical questions. If particles exist in superpositions until observed, if entangled particles can instantaneously affect each other across vast distances, what does this imply about reality itself? Are we passive observers of a predetermined universe, or are we participants, influencing the unfolding of events through the very act of observation? These questions are not merely academic, they invite a profound sense of wonder and curiosity. As you settle into this calm, reflective state, imagine the unfolding of these discoveries like ripples across a still pond. Each breakthrough, from Planck's quanta to Schrödinger's wave function, from Heisenberg's uncertainty to the entanglement experiments, adds texture and depth to the quantum tapestry. We see a universe that is both intricate and playful, mysterious and elegant, where certainty is rare and probability reigns supreme. Now consider the human element in this story. Each experiment, each equation, represents decades of creativity, intuition, and persistence. Scientists built on one another's work, testing hypotheses, challenging assumptions, and sometimes doubting themselves. In this, there is a comforting resonance for us. Discovery is a collective journey, a dance of curiosity and patience, a reminder that understanding, like a soft melody, emerges gradually, note by note. Looking forward, these developments set the stage for even more extraordinary insights. The next chapters of quantum research delve into superposition, decoherence, and the strange behaviors that emerge when observation interacts with probability. Experiments grow ever more precise, technologies ever more ambitious, and our philosophical reflections ever deeper. In essence, quantum mechanics is not a completed story, but a continuing adventure, and as observers of both science and life, we are invited to participate in the unfolding narrative. And so, as your awareness expands alongside this exploration, allow yourself to feel a quiet connection to these unseen threads of reality. The discoveries of quantum mechanics remind us that the universe is far richer, stranger, and more interconnected than our everyday experiences suggest. The principles that govern the tiniest particles ripple outward, shaping stars, planets, and perhaps even our own consciousness. Take a deep, unhurried breath and let this awareness settle. Each particle, each wave function, each entangled pair exists not just in isolation, but as part of a vast, dynamic network. And as we prepare to move into the next chapter, where we will examine the first quantum entanglement experiments and their striking implications, you can carry with you this sense of calm curiosity, wonder, and intimate connection to the universe's most subtle workings. Chapter 6: The First Quantum Entanglement Experiment. As we gently glide into the world of entanglement, let's pause to appreciate how revolutionary this idea really is. Imagine two dancers separated by miles, yet somehow every move one makes is instantly mirrored by the other. Spin to the left, and the partner spins in perfect symmetry. Twirl to the right, and the same occurs as if an invisible thread connects them. This is the essence of quantum entanglement, a relationship so intimate and instantaneous that it once left Einstein himself uneasy, calling it spooky action at a distance. The journey toward experimentally verifying this phenomenon began in the mid-20th century, inspired by the Einstein-Podolsky-Rosen paradox, or EPR paradox. In 1935, Einstein and his colleagues challenged the completeness of quantum mechanics. They argued that if entanglement were real, then information about one particle would instantaneously affect its partner, even if they were light years apart. This seemed impossible. After all, nothing could travel faster than light, according to relativity. Yet the math of quantum theory suggested otherwise. Fast forward a few decades, and physicists were ready to test these mind-bending predictions. Enter the first real entanglement experiments, where photons, particles of light, took center stage. Researchers used a process called parametric down conversion, in which a single photon enters a special crystal and splits into two entangled photons. These pairs were then sent to separate detectors, sometimes tens of meters apart, with carefully designed experiments to measure their polarization, the direction in which the photon's electric fields oscillate. The results were nothing short of astonishing. When the measurement was performed on one photon, its entangled partner seemed to know instantly, exhibiting correlated behavior even across the experimental separation. Each detection confirmed the predictions of quantum mechanics, demonstrating that the universe operates in ways that defy classical intuition. And here's the beautiful part. These correlations persisted, not just as a statistical anomaly, but as a consistent, repeatable feature of reality. To help visualize this, imagine flipping two perfectly synchronized coins in separate rooms. If the first coin lands heads, the second coin always lands heads too, even if no one communicates between the rooms. Now extend this analogy to millions of coin flips happening in laboratories around the world, and you start to glimpse the astonishing reliability of entanglement. What Einstein saw as a paradox, experimentalists confirmed as reality. But why does this matter beyond the intellectual thrill? Because entanglement is more than a quirky quirk of the quantum world. It forms the foundation for transformative technologies. Quantum cryptography, for instance, leverages entangled particles to create ultra-secure communication channels. If an eavesdropper attempts to intercept the particles, the entanglement is disturbed, revealing the intrusion. It's like a cosmic alarm system that safeguards information in ways impossible for classical encryption methods. Entanglement also underpins quantum teleportation, not the Star Trek kind that beams you across the galaxy, but the transmission of quantum states. By manipulating entangled particles, scientists can transfer the exact state of one particle to another, effectively moving quantum information instantaneously. While this may seem abstract, it's a vital step toward building functional quantum networks, linking quantum computers, and establishing a future quantum internet. Returning to the first experiments, it's important to note that they weren't perfect. Early setups faced challenges, maintaining entanglement over distance, preventing interference from environmental noise, and designing detectors sensitive enough to capture these delicate states. But physicists persevered, refining techniques with meticulous care. Every hurdle overcome brought the quantum world into sharper focus, revealing a universe more interconnected than classical physics ever suggested. One particularly elegant demonstration involved entangled photons sent along optical fibers to separate labs. Despite imperfections, correlations persisted even when the fibers bent, twisted, or extended over long distances. This indicated that entanglement wasn't fragile in the way classical systems might be. It was robust, yet profoundly non-intuitive. It seemed that reality, at its most fundamental level, obeyed rules that were simultaneously delicate and resilient, subtle and precise. Now imagine this in a human context. Think of two musicians separated by continents, playing in perfect harmony without a shared sheet of music or a conductor. Each note emerges in precise coordination with the other, as if the universe itself ensures synchronicity. This is the poetic essence of entanglement. Particles, like these musicians, behave as though they exist in a shared, interconnected reality that transcends ordinary space and time. As we reflect on these early entanglement experiments, it's also worth noting their philosophical impact. The concept challenges the classical notion of local realism, the idea that objects exist independently and are only influenced by their immediate surroundings. Quantum mechanics suggests that reality may not be strictly local. The state of one particle is tied to its partner, no matter the distance. It invites a subtle humility, a recognition that the universe operates with rules far stranger and more beautiful than our everyday experiences reveal. The first entanglement experiments, therefore, weren't just about physics. They were a window into the universe's profound interconnectedness. They invited us to ponder questions like, how do seemingly separate entities relate in ways invisible to our senses? What does it mean to be an observer in a universe where observation itself influences outcomes? These questions, while abstract, are part of the contemplative beauty that quantum physics offers, a serene meditation on the hidden layers of reality. And here's an analogy to help settle this concept in your mind. Imagine a vast, calm lake at twilight. You toss a pebble in one corner, and almost imperceptibly, a ripple emerges on the opposite side. Entanglement is like that ripple, invisible yet connected, reaching across distances instantly and subtly, reminding us that even the smallest actions can resonate far beyond what we perceive. In this sense, quantum entanglement is both a scientific discovery and a poetic lens, allowing us to glimpse the interconnected nature of existence itself. As we draw this chapter to a close, take a deep, slow breath and let the notion of entanglement settle gently into your awareness. Consider the countless entangled pairs in the universe, dancing in perfect harmony across space and time, forming the backbone of quantum phenomena. Their quiet, instantaneous connections hint at a universe that is alive with subtle coherence, inviting wonder and contemplation. And with that, we're ready to transition smoothly into the next chapter, where we'll explore quantum computers solving real-world problems, demonstrating how entanglement and other quantum principles move from abstract theory into revolutionary technology. But before we do, remember to take a moment to appreciate the beauty of discovery. A single experiment, carefully designed and patiently executed, can unveil truths that reshape our understanding of reality and our place within it. Chapter 7: Quantum Computers Solving Real-World Problems. Imagine trying to navigate a vast, intricate city with countless streets as alleys and intersections. A classical computer is like a single car, traveling one path at a time, taking each street in sequence, gradually exploring the city. A quantum computer, on the other hand, is like having an army of cars that can simultaneously explore every street, alley, and hidden passage at once, communicating instantaneously with one another. This is the power of quantum computing, and entanglement is the invisible thread that connects these quantum explorers, allowing them to perform feats impossible for classical machines. The concept of quantum computers may sound like science fiction, but it is deeply rooted in the very principles we have already explored: superposition, entanglement, and probability waves. In classical computing, bits exist in one of two states, 0 or 1. Quantum computers use qubits, which thanks to superposition can exist in multiple states at once. Couple that with entanglement, and qubits can coordinate in ways that scale exponentially with the number of qubits. A system of just 50 qubits can represent more states simultaneously than there are atoms in the observable universe. It's mind-boggling, yet entirely real. But why do we care about this immense parallelism? Because certain problems, even seemingly simple ones, are staggeringly complex for classical computers. For example, optimizing traffic flow in a megacity, predicting molecular interactions for new drug designs, or cracking cryptographic codes all involve an astronomical number of possibilities. Classical computers would take millions of years to process these efficiently. Quantum computers, with their ability to explore many possibilities simultaneously, offer a shortcut through this complexity, a direct path through the combinatorial jungle. One particularly vivid illustration comes from chemistry and material science. Imagine trying to understand how a single molecule interacts with thousands of others in a chemical reaction. Classical simulations often fail due to the exponential growth of possible interactions. Quantum computers, however, can simulate these quantum systems directly. By encoding the molecule's quantum states into qubits, researchers can model reactions with unprecedented accuracy. This isn't just theory. Quantum simulations are already helping chemists predict new materials, design more efficient solar cells, and even develop novel pharmaceuticals. Another domain benefiting from quantum computing is optimization problems, which appear in logistics, finance, and artificial intelligence. Suppose a delivery company wants to minimize travel distance while visiting hundreds of locations. The number of possible routes grows factorially, quickly exceeding classical computing limits. Quantum algorithms, like the Quantum Approximate Optimization Algorithm, QAOA, allow the system to explore a vast landscape of possibilities simultaneously, identifying near-optimal solutions much faster than traditional methods. In essence, quantum computers can find the best path through a forest of choices, using the rules of quantum mechanics as a guide. Let's take a step back and imagine this visually. Picture a massive, foggy forest with countless paths, each representing a possible solution. Classical explorers walk one path at a time, marking their way and backtracking when necessary. Quantum explorers, thanks to superposition, simultaneously inhabit multiple paths, sensing where the clearings and obstacles are, coordinating through entanglement to converge on the most promising routes. This analogy captures the essence of quantum computing, parallel exploration guided by interconnectedness. Entanglement plays a pivotal role here. It allows qubits to remain correlated even when separated, ensuring that changes in one qubit can influence its partners instantaneously. This correlation isn't about faster-than-light signaling in the classical sense. It's about shared information encoded in the quantum state. Think of entangled qubits as synchronized dancers on a vast, invisible stage, each movement reflecting the others in harmony. In a quantum computer, this harmony is what allows computations to scale efficiently and coherently, achieving results unattainable by classical means. Yet building and maintaining quantum computers is no trivial task. Qubits are fragile, easily disturbed by their environment, a phenomenon known as decoherence. Imagine trying to balance a spinning top on a trampoline in the middle of a storm. Any external disturbance can knock it off. Physicists combat this by isolating qubits in ultra-cold environments near absolute zero, shielding them from vibrations, electromagnetic fields, and even stray cosmic rays. The engineering challenges are immense, but the potential rewards, new drugs, optimized systems, and breakthroughs in fundamental science make the pursuit compelling. Real-world quantum computing applications are already emerging. Google's Sycamore processor famously performed a computation in 200 seconds that would take the fastest supercomputers thousands of years. While this quantum supremacy demonstration focused on a contrived problem, it proved that quantum computers could, in principle, outperform classical counterparts in specific domains. Companies like IBM, Rigetti, and IonQ are developing cloud-accessible quantum processors, allowing researchers and enthusiasts to experiment with quantum algorithms remotely, further accelerating discovery. Quantum computing isn't only about raw speed, it's about redefining problem solving. Traditional approaches often rely on approximations, heuristics, and simplifications because the computational load is too high. Quantum computers, by exploring multiple possibilities simultaneously, allow for more precise and holistic modeling, whether simulating chemical reactions, optimizing traffic flows, or exploring financial markets. Quantum computing opens doors to solutions previously out of reach. Now let's make this a bit more tangible. Imagine trying to solve a massive jigsaw puzzle, but instead of placing one piece at a time, every piece simultaneously tries every possible position. Eventually, the puzzle solves itself almost instantaneously. That is, in a simplified sense, what quantum computers do with complex computational problems. The puzzle pieces are the qubits, entangled and exploring possibilities in a superposed state until the solution emerges as a pattern in the measurement outcomes. Another fascinating application comes from quantum machine learning. Traditional AI systems rely on classical data representations and algorithms. Quantum computers can encode data into high-dimensional quantum states, allowing machine learning models to detect patterns and correlations that would remain invisible classically. This could revolutionize fields like drug discovery, climate modeling, and financial forecasting, where understanding complex interdependencies is crucial. Despite the promise, quantum computing is not a panacea. Many practical problems still require hybrid approaches, combining classical and quantum resources. The field is evolving rapidly, with breakthroughs in error correction, qubit design, and algorithm development, bringing us closer to practical, large-scale applications. Yet even in its current form, quantum computing challenges our understanding of computation itself, blending physics, mathematics, and engineering in ways that are both profound and poetic. As we reflect on quantum computers solving real-world problems, it's worth considering the philosophical implications. These machines operate not by linear logic, but by embracing uncertainty, probabilities, and interconnectedness, core principles of quantum mechanics. They remind us that reality itself is not rigid or deterministic, but a dynamic web of possibilities, waiting for observation and interaction to shape outcomes. In a sense, quantum computers are a tangible manifestation of the quantum universe, where uncertainty is not a flaw, but a resource. Before we move to the next chapter, take a moment to appreciate the elegance of this technology. Every quantum processor Every entangled pair of qubits represents humanity's effort to harness the strange and beautiful rules of the quantum realm. They are both a tool and a meditation, revealing how deeply our universe is woven with subtle connections, probabilities, and mysteries. By observing and interacting with these systems, we glimpse the hidden rhythms of reality, one qubit at a time. Chapter 8: Loopholes of Quantum Entanglement. Quantum entanglement, often called spooky action at a distance by Einstein, is one of the most mesmerizing phenomena in physics. Two particles, no matter how far apart, can remain instantaneously correlated. Measure one, and you immediately know the state of the other. At first glance, this seems to violate common sense, even threatening the classical idea that information cannot travel faster than light. Yet this is not a loophole for instant communication. Rather, it is a window into the deeply non-local nature of reality. But here's the twist: proving entanglement isn't as straightforward as it sounds. Experiments must account for loopholes, tiny gaps or imperfections in experimental design that could, in principle, explain correlations without invoking genuine entanglement. Think of it like trying to detect a whisper across a crowded, noisy room. You need to be sure the sound isn't coming from a hidden speaker or being echoed in some unexpected way. Similarly, physicists must rule out any classical explanation that could mimic entangled correlations. One of the first and most significant loopholes is called the detection loophole. In quantum experiments, detectors aren't perfect. They sometimes fail to register a particle. If only a subset of particles is detected, one could argue that the observed correlations might not represent the whole system, leaving room for classical explanations. Addressing this loophole requires high-efficiency detectors and careful statistical analysis to ensure that the correlations are genuine. Another major challenge is the locality loophole. To claim true entanglement, measurements on the two particles must be conducted far enough apart so that no signal traveling at the speed of light could influence both outcomes. Imagine two dancers performing in separate arenas, thousands of miles apart. If one dancer's move could somehow instantaneously signal the other, you wouldn't be witnessing spontaneous synchronization. It could be a clever trick. Physicists solve this by ensuring space-like separation, meaning the measurements are completed faster than any signal could travel between them, preserving the integrity of the entanglement. Then there's the freedom of choice loophole, a more subtle but equally fascinating issue. It asks whether the choice of measurement settings might somehow be correlated with hidden variables in the particle's past. In other words, could the universe be conspiring to produce correlations that appear entangled, even if nothing spooky is happening? To close this loophole, researchers have designed experiments using random inputs that are as independent as possible from the system being measured. This can involve quantum random number generators or even cosmic sources like starlight from distant galaxies, ensuring that measurement choices are genuinely free and uninfluenced by local factors. This is where the Canary Islands experiment comes into play, a groundbreaking study that pushed the boundaries of our ability to rule out these loopholes. Physicists used quasars at opposite ends of the observable universe to generate random measurement settings. The light from these quasars traveled billions of years before reaching Earth, effectively guaranteeing that no hidden variables in the particle's past could influence the experiment. In essence, the universe itself became a cosmic referee, ensuring that the entanglement observed wasn't a clever trick of classical physics. The results were stunning. The experiment further confirmed that entanglement is real, not an artifact of imperfect detection or hidden influences. The correlations observed matched the predictions of quantum mechanics with extraordinary precision, leaving alternative explanations increasingly untenable. This wasn't just a validation of a theory, it was a profound glimpse into the fundamental non-locality of the universe, showing that reality itself is intertwined across vast distances and timescales. Yet even with such meticulous experiments, loopholes remain a rich area for exploration. Each experiment improves upon the last, refining techniques, increasing detector efficiency, and pushing measurement separations to ever greater scales. These refinements aren't just technical exercises, they deepen our philosophical understanding of reality. Quantum entanglement challenges the classical notion that the universe is made of independently existing parts. Instead, it suggests a connected cosmos, where the state of one particle can instantaneously relate to another, no matter the distance. Let's bring this down to an intuitive analogy. Imagine a pair of perfectly synchronized watches, created at the same factory, then sent to opposite ends of the planet. When you glance at one watch, you instantly know the time on the other. Classical physics could explain this if both watches were pre-programmed. But entangled particles are even more mysterious. They aren't preset. Their states aren't determined until measurement, yet once one is observed, the other reflects that choice immediately. It's as if the universe is coordinating outcomes across space and time in a way that defies classical intuition. Entanglement also opens doors to quantum technologies. Secure communication, for instance, leverages the unique properties of entangled particles. Any attempt to eavesdrop on a quantum channel introduces detectable disturbances, ensuring that information remains private. This principle underpinned quantum cryptography, offering security far beyond classical limits. Similarly, quantum networks and teleportation experiments use entanglement to transmit states of particles instantaneously across distances, creating the foundations of future quantum internet systems. Even philosophical implications abound. Entanglement challenges our understanding of locality, causality, and the nature of reality itself. It raises questions like, are objects truly independent, or is there apparent separateness and emergent illusion? How does information propagate in a universe where particles can reflect each other's states instantaneously? These aren't just abstract puzzles. They touch on our deepest assumptions about space, time, and existence. Yet the beauty of studying loopholes is that it emphasizes humility and rigor. Quantum mechanics may be strange, counterintuitive, and even spooky, but scientists meticulously check every detail, probing for weaknesses, ensuring that extraordinary claims are supported by extraordinary evidence. This commitment to precision mirrors the scientific method itself, a careful dance between imagination and discipline, where each experiment is a step deeper into understanding reality's underlying patterns. As we contemplate entanglement and its loopholes, it's worth noting the human element in this grand exploration. Designing experiments to test non-locality, deploying equipment in remote locations like the Canary Islands, and interpreting results with painstaking care. All of this represents a collaboration across continents, generations, and disciplines. Quantum entanglement, once a theoretical curiosity, has become a bridge connecting not just particles across space, but people across cultures, united in curiosity and wonder. In closing this chapter, imagine standing under a clear night sky, gazing at stars billions of light years away. Somewhere out there, particles emitted from distant quasars are entangled, connected across unimaginable distances. When we observe a particle here on Earth, we are participating in a cosmic conversation, a dialogue that transcends time and space. It's a poetic, humbling reminder that physics is not just about equations. It's about uncovering the deep interconnectedness of the universe. Chapter 9: The Results of the Canary Islands Experiment. The Canary Islands experiment was a true milestone in the quest to understand quantum entanglement. By using quasars on opposite ends of the universe to generate random measurement settings, physicists aimed to close the last significant loopholes and test the very fabric of reality itself. But what did the results actually reveal, and why do they matter so much? Let's unpack this with care and imagination. First, consider the experiment's design. Researchers placed detectors on two separate islands, La Palma and Tenerife, separated by about 100 kilometers. At each detector, particles, specifically photons, were measured in randomly chosen ways, with the random choices determined by the arrival of ancient light from quasars. These quasars emitted their light billions of years ago, long before the Earth or humans existed. Using this cosmic randomness meant that the freedom of choice loophole, the idea that the measurement settings could somehow be influenced by hidden variables, was effectively closed. The universe itself ensured the measurements were independent. Now, let's dive into the results. The correlations observed between entangled photons were perfectly consistent with the predictions of quantum mechanics. The two particles acted in unison, reflecting each other's states instantaneously, even though they were measured across great distances. Classical physics, which relies on local hidden variables or pre-programmed states, could not account for the observed correlations. In other words, the spooky action at a distance that Einstein once doubted was real, and any alternative classical explanation was effectively ruled out. To understand the significance, imagine flipping two coins on opposite sides of the globe. Normally, each flip is independent, and the outcome of one coin has no influence on the other. But in entanglement, flipping one coin instantly determines the outcome of the other, as if they are connected by an invisible, instantaneous thread. That's what the Canary Islands experiment confirmed, but on a cosmic scale. Another striking aspect of the results was their statistical robustness. Thousands of photon pairs were measured, and the data repeatedly violated Bell's inequalities. These mathematical inequalities are a critical test for distinguishing quantum entanglement from classical correlations. Violating them means the particles are genuinely entangled, not simply coordinated by hidden variables. The Canary Islands experiment achieved a level of precision and scale that previous tests could only aspire to, setting a new gold standard for quantum experiments. Beyond the numbers and graphs, the results carry profound implications for technology. Quantum entanglement isn't just a theoretical curiosity. It underpins the next generation of quantum technologies. Quantum computers, for instance, exploit entanglement to perform computations that would be impossible for classical machines. Secure communication via quantum key distribution leverages the fact that any attempt to eavesdrop on entangled particles introduces detectable disturbances. The Canary Islands experiment strengthens the foundation for these technologies, confirming that entanglement is real and reliable even under the most rigorous tests. But let's step back and consider the cosmic perspective. Using quasars that emitted light billions of years ago ties this experiment not just to the quantum realm, but to the history of the universe itself. When scientists measured entangled photons here on Earth, the choices of measurement were influenced by events that occurred long before our planet existed. It's almost poetic. The universe, stretching across billions of light years, participates in a delicate experiment that confirms the fundamental interconnectedness of reality. In essence, we are witnessing a conversation between the infinitely large and the infinitesimally small. The results also help clarify lingering philosophical questions. Quantum mechanics has long challenged classical intuitions about causality and locality. The Canary Islands experiment reinforces the idea that reality is non-local, meaning that parts of a system can be instantaneously correlated across space in ways that classical physics cannot explain. This non-locality doesn't allow faster than light communication, preserving relativity, but it does reshape our understanding of what connected truly means in the quantum realm. Moreover, the experiment exemplifies the careful interplay between theory and observation. Quantum mechanics predicts entanglement with extraordinary precision, but each new experiment tests those predictions against the complexities of the real world. By using ancient cosmic light to control measurements, the Canary Islands team added an elegant and unprecedented level of rigor. This is science at its most meticulous, layering imagination, creativity, and technical mastery to probe the deepest mysteries of existence. To make this more intuitive, consider an orchestra playing across two separate concert halls, thousands of miles apart. Each musician receives a note sheet determined by signals from distant stars, and yet the music emerges perfectly synchronized. No classical mechanism could explain the coordination, yet it unfolds flawlessly, echoing the predictions of quantum theory. That's the essence of what these experiments reveal: an underlying harmony in the universe, one that defies ordinary logic, but manifests with astonishing consistency. Finally, the results open doors to even more ambitious experiments. If entanglement holds across cosmic distances and time, could it be used to probe the structure of space-time itself? Could we one day use entangled particles to test the interplay between gravity and quantum mechanics? The Canary Islands experiment is not the end of the story. It is a milestone pointing toward the next frontier, where quantum phenomena intersect with cosmology, computation, and even our deepest philosophical questions about reality. In conclusion, the Canary Islands experiment didn't just confirm that quantum entanglement is real. It illuminated the profound interconnectedness of the universe, tested the boundaries of physical law, and provided a platform for future technologies. By cleverly leveraging cosmic randomness, scientists closed loopholes that have puzzled researchers for decades, offering one of the clearest windows yet into the mysterious dance of entangled particles. For anyone intrigued by the intersection of science, philosophy, and wonder, these results are a thrilling testament to the beauty and strangeness of our universe. Chapter 10: Quantum Entanglement in Modern Physics. Quantum entanglement has evolved from a theoretical curiosity into a cornerstone of modern physics. What Einstein once skeptically dubbed spooky action at a distance is now not only experimentally verified, but also increasingly applied in practical and theoretical frameworks that shape our understanding of the universe. In this final chapter, let's explore how entanglement fits into today's physics landscape, technology, and philosophical inquiries, and why it continues to fascinate scientists and dreamers alike. First, consider the sheer scope of entanglement's relevance. It's not confined to laboratories or abstract equations. It permeates multiple fields of research. In quantum computing, for instance, entangled qubits allow parallel computation on an unprecedented scale. Unlike classical bits that are strictly 0 or 1, entangled qubits can exist in superpositions, enabling a single quantum computer to explore multiple solutions simultaneously. This is more than a technological novelty. It's a revolution in problem solving. Imagine trying to find a needle in a trillion haystacks. Classical computers would search one by one, but an entangled quantum system effectively examines all haystacks at once, thanks to the interconnection of qubits. Entanglement also underpins quantum cryptography, providing an unbreakable level of security rooted in the laws of physics rather than human ingenuity. Any attempt to intercept or measure entangled particles alters their state, immediately revealing tampering. This is a profound shift from classical encryption methods, which rely on complex algorithms that could eventually be broken with enough computational power. With entanglement, the security is intrinsic, built into the very behavior of the universe. It's like sending messages on invisible threads that snap and alert you if anyone touches them. Beyond technology, entanglement has become a tool for probing fundamental physics. Researchers are exploring whether entanglement could reveal hidden structures in space-time, or whether it can be linked with gravity in a unified framework. Some theoretical physicists propose that the fabric of space-time itself might emerge from networks of entangled particles, suggesting that entanglement is not just a curious feature, but a foundational aspect of reality. In this view, the universe is not a collection of isolated points in space, but a vast tapestry of connections woven together by the threads of quantum correlation. Modern experiments continue to push the boundaries of what entanglement can do. Satellites have demonstrated entanglement across hundreds of kilometers, opening possibilities for global quantum communication networks. On Earth, laboratories are working with ever more complex entangled systems, linking multiple particles in intricate patterns that could lead to fully operational quantum computers. Each step confirms the predictions of quantum mechanics while also expanding our conceptual horizon. Entanglement is not a rare or fragile phenomenon. It is robust, scalable, and in a sense, universal. Philosophically, entanglement challenges our intuitive understanding of reality. Classical physics taught us that objects have independent existences, influenced only by local forces. Entanglement tells a different story. Two particles, no matter how far apart, can behave as a single, inseparable system. This idea extends beyond physics, nudging us to rethink concepts like causality, locality, and even individuality. If particles separated by billions of light years remain connected, what does that say about the nature of connection in the universe at large? Could entanglement hint at deeper interconnections, not only in matter, but perhaps in consciousness or life itself? To make this more tangible, imagine the universe as a vast, invisible web. Each node represents a particle, a star, or even a quantum system, and each strand is an entangled connection. Pull on one node, and subtle vibrations ripple across the web, instantaneously affecting distant nodes. These ripples do not transmit energy in the classical sense, but they encode correlations that are essential to the system's structure. Observing entangled particles, then, is like glimpsing the hidden wiring of reality itself. Entanglement also enriches our understanding of causality and time. Experiments such as delayed choice entanglement swapping suggest that events in the present can influence correlations established in the past. While this doesn't violate relativity or allow backward in time communication, it does upend classical notions of linear causation. The universe, at its most fundamental level, appears less like a clockwork machine and more like a dynamic, interconnected network of possibilities where observation and correlation co-create reality. The cultural impact of entanglement shouldn't be underestimated either. It has inspired art, literature, and philosophy, becoming a metaphor for connection, intimacy, and the unseen forces that bind reality together. From science fiction, writers imagining instantaneous communication across galaxies, to philosophers pondering the nature of consciousness, entanglement serves as both a scientific fact and a poetic lens through which we view the universe. Yet, as robust and verified as entanglement is, it continues to spark curiosity and humility. Each experiment raises new questions. How far can entanglement be maintained? Can it be scaled to macroscopic systems? Could entanglement play a role in biological processes, as some studies suggest with photosynthesis or avian navigation? Scientists remain explorers in an uncharted realm, continually testing the boundaries of what is possible. In conclusion, quantum entanglement in modern physics represents a bridge between theory, experiment, technology, and philosophy. From the Canary Islands experiment, confirming Einstein's spooky action, to cutting-edge quantum computers and global communication networks, entanglement is no longer a speculative idea. It is a demonstrable, exploitable feature of reality. It challenges our intuition, expands our technological capabilities, and invites us to see the universe as a web of subtle, astonishing connections. Before we close this journey, remember the wonder of what we've explored. The particles that mirror each other across space, the cosmic quasars that governed measurements billions of years ago, and the principles that suggest reality itself is woven from the fabric of correlation. If you've enjoyed this exploration, subscribe to Sleep Entangled for more journeys into the mysteries of quantum physics, consciousness, and the nature of existence. Together, we'll continue to explore, wonder, and gently drift into the profound calm that comes from understanding the universe's most subtle truths. Rest now and let the interconnected dance of quantum particles inspire dreams as vast and mysterious as the cosmos itself.